Hello, and welcome to another brief video lesson, Photometry and Overview. The science of photometry is measuring the changes in flux from one object or objects to better understand what the nature is that you're observing. As a brief reminder, luminosity is the power output of an object at its source. Flux is what we receive here on Earth. There's a difference based on distance. The farther away it is, the less flux is received from a particular object. We measure this change. This could be a variable star, eclipsing binary, exoplanet, quasar, supernova, nova, blazar. Any number of targets can be useful for photometry. This image you see here is from Astronomy Photo of the Day. The flickering lights are RR Lyrae stars that are varying their brightness over the course of the exposure of this globular cluster. We can measure the distance to these RR Lyraes through the use of photometry. In the context of astronomy, photometry is measuring how much light is reaching us. The light received from the object depends on several factors, including its intrinsic power, its luminosity, the distance of the object, the observing conditions on Earth, air mass, clouds, sky, what have you, and the exposure time of your camera. From photometry, we can learn more than what the star is doing at a certain time. We can learn the circumstances under which it was born. We can learn how it evolves, how it dies. Let's take, for example, here this galaxy. There are variable stars that we use photometry on called Cepheid variables that from its light curve, we know the distance to this. And you can measure the distance to galaxies by measuring that. Globular clusters, as we just saw in the last image, are home to RR Lyraes, which are useful in measuring their distance as well. This image here is the Pleiades, the Seven Sisters, which are all variable stars in their own nature, fresh out of the stellar birthplace, and this is an example of what a light curve looks like. So why we study photometry? Because it reveals important information about the objects being observed, and it can provide temperature information through colors, distance and mass information of stars studied in clusters, structure and character of stars, constraints on models of stellar evolution by observing the output at various light wavelengths. And we can also find asteroids, comets, supernovae, novae, all through photometry. Back to the RR Lyrae example. This is a typical RR Lyrae light curve of its output. It's a rapid increase in brightness by a fall off. By a rapid increase by a fall off. It looks like a stair. And in the image you see on the right, that's the variation that these are going through. They get bright and then they come down over time. And what you can do then is you can measure that period, get its brightness, understand its true luminosity, its true output, and from that we use the distance modulus to tell how far away it is. Cepheid variables we talked about here are the other. In fact, Cepheids, through photometry, is how we discovered that the Milky Way galaxy is just one of a billion galaxies. Edwin Hubble helped us understand that. There are types of photometry. There's absolute. Determine the actual magnitude of an object observed by comparing the star to a photometric standard. So if I want to look at a star and say, what magnitude is that? I can image that with my CCD camera and filters, get a magnitude, compare that to a standardized star through my standard filter set, and I can do a comparison to understand what its true magnitude is. Differential photometry. This is where what we do often in exoplanets. This is where we find what's called a comparison star, and that's a star of zero change in magnitude. It's flat. And then we look at the variable star, could be an exoplanet host, any number of stars, and we watch how its light changes over time. The comparison star really has no brightness change, but the variable star compared to that will go up and down in terms of relative brightness. This is differential photometry, the difference between the two. Relative photometry is getting an instrumental magnitude, which means the magnitude that I got in my CCD image. And it's comparing a target to another known comparison object that is not in the field of view. Could be somewhere else in the sky, but I need to compare two different pictures to get and understand what my brightness is. Common definitions you'll hear us talk about in photometry. One is the background. That's this grayish junk right here. That's sky background, and that is noise. It's from the moon, street lights, dust in the atmosphere, you name it. Counts. Counts are the number of photons within a given circle. So here we've got an aperture around this one star, and the appropriate counts would be how much light hit each pixel within that area. That's a count. A comparison star is a star whose brightness does not change over the course of your series of images. It stays stable, one night to the next, on and on. A standard star is similar to a comparison star, but it is measured through a sky survey, either a Landholt standard or an AAVSO Arne Hindren standard star, by which we know what the magnitude should be through a filter set. It then allows us to measure our set compared to standardization and get true values that way. Performing photometry, the process overview. The key components are you need a CCD camera, you need a telescope with a great mount, and you need to view an object that's not sitting down on the horizon but is up higher in the sky. During the image, we measure the number of photons received. Take this right here. It's a great example of a CCD chip with multiple pixels, and each of those pixels have differing values for the light that has been received, and that's what a CCD does. We then measure a comparison star and a variable star in the same image. We have to calibrate the images to standardize the image set, to get rid of all the junk. We have to turn the measurements into a physical measure of brightness, and we repeat this over and over and over again. We can't do it from just one image, really. Well, we can get some magnitudes, but to get a photometric light curve, something like you see here, you have to have multiple images. And in each one of those images, the photometric star, the variable you're measuring, will fluctuate. And that plot is a measurement of that fluctuation. So photometry allows us to learn about the nature of objects by measuring the output of light. Using a CCD telescope, a good mount, standardized filter, we can determine stellar types, temperatures, distance, exoplanet transfers, their orbits, distance to globular clusters and open clusters, distance to galaxies. Photometry is the cousin of astrometry. Most astronomical science is performed in the field of photometry and will be a major focus of Brief going forward. Appreciate your attention. We'll see you on a future Brief video lesson.